We have introduced the candle flame as example for diffusion flame, but basically those kinds of combustion structures is very hard to use for the real application because for the combustion process, typically for the candle flame, it's basically controlled by diffusion transport. And you can see the flame height for given candle flame, even you increase the size of your candle, the flame height is still small, right? And then they cannot have a big energy supply coming out from the burning of the candle. Now people think about, can we enhance those kinds of burning intensity for a given diffusion flame? That means that if you try to introduce the gaseous fuel or maybe the liquid fuel into your combustion chamber and burn it as a diffusion flame, what kinds of combustion characteristics we need to look at it and carefully manage it. Now, the idea is if you use, for example, in the beginning, we try to think about if you use the gaseous fuel and you inject into the combustion chamber, very similar way as the jet injections. For example, here for the real application in industry sites, they will inject gaseous fuel jets along a tube, a single tube, but usually they will accompany with the surrounding air coming out. Then we call this a so-called coaxial jet burner. Coaxial jet burner in the inner jet, that is, then you may have, for example, the natural gas or propane injecting out, and you will have surrounding air coming out, and they will meet together and interface of the inner and outer jet. And the flame, usually they will sit very closer to the interface of this inner and outer jet. Okay, since this is quite different from the candle flame. The fuel supply for candle flame, basically they come in from the center wick, right? And those liquid wax will evaporate coming out by diffusion from the center wick to the surrounding. And those kinds of evaporation rate is small, is relative small, and cannot compare with the momentum of a given fuel jet coming out from the burner and induced by the pressure gradient, because the fuel can be injected out to the longer distance, and you will produce a longer flame length and to extend the heating area. Later on, I will tell you how the flame length change with increasing the flow momentum or flow injections. Okay, you can see by these figures, actually you can produce a so-called diffusion flame, and those diffusion flame will extend to a longer distance. And by looking at this, the structure is very similar to the structure for a candle flame. The major difference here, for the candle flame, the interior of your diffusion flame basically is controlled by the fuel molecule diffuse from the center to the outer surrounding, right? But for the jet flow, they have some overall a buck convective flow coming out, and they will push your gaseous molecule to move very fast to the further downstreams. And those supply of the gaseous fuel will give you have a large amount of heat may be released from the flame. But in the structure is you can have a buck flow moving around the actual positions. The fuel inside of your diffusion flame, they still should be controlled by the diffusion process. The fuel will diffuse into the outer surrounding. They will meet with oxygen coming from the air, the oxygen in the air to meet together at the diffusion flame. Okay, the only difference for the jet diffusion flame with the candle flame, mainly we introduce the flow convection into the jet flow. to make more fuel can be supplied to enhance the burning to release more heat. Those enhancements of the coolant convection will give you a possibility to extend your combustion intensity for overall jet diffusion flame compared with the candle flame. Okay, but before we jump to detailed descriptions on the variation of a jet diffusion flame, we need to go back a little bit to review the cold flow structure for a given cold jet. Okay, I think you understand the these pictures these figures I already introduced earlier, and this is the jet flow, and you understand there is some there is a flow structure divided by three regions. One is the potential cone, and there is the intermediate transition region. Then finally, they will go to the fluid developed zone, right? And the potential cone, usually we use it to analyze the position of your premise frame, because premise frame is determined by the balance of the supply velocity and the frame speed. Usually they are small. Okay, the frame length is small. I hope you remember it and you learn it from previous section for premise burning. And those descriptions basically starting from this kinds of explanation. And basically those kinds of structure based on the you have a uniform injection velocity at the exit plane of your jet. Okay. Now I give you some experimental measurement by our group to look at the cylindrical jet with the fully developed velocity profile. And then maybe I give you this description on this plot at first. Okay, here you can see uh, we use the round jet, okay, and do the measurement. Then you will use the cylindrical coordinate systems, and you can see the horizontal axis represent the radius of the position of the measuring position. We use the non-dimensionalization with the diameter of the jet, okay, and the vertical axis represent represent the actual velocity and normalized by the that value at the center, okay. The cylindrical jet, we have a center locations. We do the measurement for that and do the non-dimensionalization for each actual velocity, also the radial velocity. Now you look at for the x is the actual coordinates. Okay, when you do the measurement for the actual the actual velocity distribution at the position very close to the exit plane. For example, x equal to 5, very close to the exit plane. You can see this is an open circle like this. Okay, you can see this is an open circle. Actually, this plot, these curves represent is a parabotic shape. It's a fully developed velocity profile. Since in our experiment we use a long tube, okay, and the air inside the tube go through a long tube, then finally they will reach to the fully developed velocity profile for tubing. Then the velocity profile out of the jet will give you the nicely parabotic shape. Okay, this is the velocity profile, actual velocity profile at the x equal to 5. And you can see here, okay, for the radial velocity, actually since at x equal to 5 already has a small distance away from the exit plane. If you do the measurement at x equal to 0, then you can find out we may not have the radial velocity. But in the experiment, you cannot do the measurement very closer to x equal to 0 because the burner edge will broke has some as a limitation to let the laser sheet moving at the, to have a cross point at the center. Then we do not have any experiment data measure as x equal to 0. But for the x equal to 5, you can see the radial velocity start to increase, and they will increase a little bit higher near the edge of the jet. Okay, and this jet, this experiment basically we are looking at the so-called a single jet. Single jet means that we just impinge out the air coming out from the tube in the stagnant environment. Okay. And you can see if you increase the your actual position from 5, 20, 40, and 60, you can see the radial velocity distribution gradually they will expand the distribution along the radial direction, right? Finally, when you go to the very far downstream, x equal to 150 millimeter, you can see this basically tell you the velocity distribution in the fluid bed region of this jet flow. Okay, and similar way, you can see the radial velocity will continuous grow because the region of your jet extends to the radial directions as we described earlier in the jet flow. Okay. And you can see if you look at the velocity variation along the center line only, then this plot tell you this is x, the variation of actual coordinate from the burner exit to the very far downstreams. Initially, here you can have equal to 1 for the actual velocity, uc divided by ui. Ui is the initial velocity at the exit plane. Okay, surely you can this should be equal to 1. Okay, because at the x equal to 0, actually we do not measure it just as equal to 0 millimeter. There is a certain distance as I described at x equal to 5 millimeter is the starting point, but the value is very closer to the injection velocity, but those value will continuously decrease, okay, along the center line. This tell you the actual momentum reduced. When you move to the downstream side, those kinds of momentum will convert to radial momentum to extend your jet area, jet area to the outer surrounding. Okay, and here you can see we also do the velocity fluctuation here. Okay, radial velocity fluctuation, actual velocity fluctuation u prime, radial velocity fluctuation v prime. Then you will find out in the near field of the burner, they are small, but later on they will grow to a certain near constant value. This is a typical velocity variation for a single jet. But for real applications, usually you should consider the coaxial jet. Then we do another experiment, try to introduce the outer flow to meet with the inner jet, and this is a coaxial jet. And R basically is a ratio between the velocity ratio between the inner jet and the outer jet. I will not explain this to detail, but you understand in this case we have the outer jet with a small injection velocity compared with the velocity in the inner jet. Okay, and they will have some interaction near the interface of inner and outer jet. And this plot is similar way they tell you the center. Around the center line, the actual velocity drops continuously, and you can see this variation are quite close even for the velocity fluctuation for actual velocity, and for radial velocity, they show very similar way because we are doing measurements around the center line. The flow condition in around the center line is protected by the overall jet, has a small influence coming from the outer flow. Okay, but for the detail, you can see there is some differences. You can see for the similar representations, here we use the DI as the non-dimensional value still represents the radial distance, and we present the non-dimensional actual velocity and also radial velocity in these figures. Okay, at x equal to 5 millimeter, very close to the exit plane of this coaxial jet, you can see there is very similar profile compared with the single jet. This is a parabatic shape, okay? But in the outer flow, actually, there's still another parabatic flow, right? Because for the outer jet, we have a larger diameter, and they will extend to a longer radial distance. But initially, when they inject it out, there's a big jump, okay, because we have a larger velocity inside in the inner jet and a smaller velocity in the outer jet, and they have a big differences. And this open circle represents the initial velocity distribution for this coarse jet. Okay, and actual radial velocity still tell you near the interface of inner and outer jet, we can see there is a increase of the radial velocity at the interface, but be pretend by the outer flow, but outer flow still have a tendency to extend their radial velocity out. Those kinds of gradient exist in the interface on the interface of the inner jet and outer jet, but those interaction will be smoothed out gradually when you move to the downstream side. Later on, these two jets actually they will mix together. In this example, we use the same the gaseous medians. Inner jet is air, outer jet is air too. Then finally, they will mix together to produce uh, this similarity curves for the fully developed region. Okay, they will grow. When you move to the downstreams, they will show you the same distributions. And here, radial velocity give you the same distribution, very similar to the single jets. Okay. But anyway, those kinds of velocity flow velocity measurements of a given cold flow give you an idea. If you do the analysis, even for the numerical calculation of theoretical prediction, usually you will have this plot, as I mentioned before. When you look at the whole flow structures, do the non-dimensionalization for temperature distributions, for your mass fraction for fuel or oxygens, and for the velocities, actually, we are looking at the cold flow. Okay, even you will have a fuel and oxygen, we assume there is no reactions. We just looking at the convection balance with diffusion. Okay, the temperature T minus T infinity divided by Ti minus T infinity. If T infinity means the temperature in the outer surrounding, Ti is the initial temperature. Now, those temperature variation and fuel, for example, you inject the fuel in air environments, there is a fuel concentration gradient and also air concentration gradient. Then those kinds of diffusion process will give you some uh, similar results. For the temperature, you have a thermal diffusion, and for the YF, you need to consider the mass diffusion, and U divided by UI, you have a momentum diffusion. When you assume those number, I hope you remember Schmidt number, Prandtl number, Lewis number. If they are the same, then you can conclude the same result like this. Okay, they tell you if you have a uniform velocity profile and a uniform temperature, uniform concentration profile, and this jet impinge out, originally you may have a potential cone here to remain all the quantities the same as the condition at the exit plane, but later on they will expand. Okay, the actual properties will convert to the radial directions, then the size of your jet will expand. Okay, and from the analysis you can find out if you compare the property at different position with the original position at the exit plane, then you will have the ratio. For example, zero point 0.9 means the quantity is just 90% of the original quantity. Gradually, those quantity will continue to reduce up to zero. What is the meaning of zero? Zero means the boundary between this jet and the outer surrounding. Okay, and we say this is a so-called ISO 9, including the isovelocity line, isothermal line, and the isocomposition contour, okay, in a laminar planar jet, okay. Based on these iso lines, we can have some idea to identify the position of your diffusion frame. And I will give you the more descriptions to look at the combustion characteristic of a jet diffusion frame for the next video.